Question 6 deals with problems that have to be solved by the use of a technique known as implicit differentiation. Implicit differentiation is used when we have a relationship between two variables, x and y, and we are unable to solve for y in terms of x explicitly, or possibly we choose not to solve for y in terms of x explicitly. Now, sometimes in solving for y in terms of x, you can get several different functions out of the same relationship. As an example, let's look at problem 6a. In 6a, we have a relationship. X squared plus y squared equals 25. In fact, you probably recognize that. That's a circle, centered at the origin, having radius 5. Now, we could solve this for y in terms of x, but we don't have to in order to find the derivative of y with respect to x. But if we're going to use implicit differentiation, what we must keep in mind at all times is that we really have y as a function of x. So when we look at y squared, we're really looking at some function of x squared, which means if we take the derivative, we're going to have to use the extended chain rule. Now, we're asked to find the slope of the tangent line to this curve at the point 3, 4. The slope of the tangent line, remember, means the derivative evaluated at that point. Now, let's try to use implicit differentiation to find that derivative. Here we have x squared plus y squared equals 25. Since this side is equal to this side, their derivatives are going to be equal. So we take the derivative of x squared with respect to x, remember. The derivative of x squared we know is just 2x. Plus, we take the derivative of y squared. But remember, y is some function of x. So the derivative of y squared has to be obtained by using the extended power rule or chain rule. So the derivative of y squared is 2y times the derivative of y with respect to x. So it's 2y times dy dx. And this is equal to the derivative of 25. Well, 25 is a constant, and its derivative is 0. So here we have a little equation, 2x plus 2y dy dx equals 0. And we can solve this equation for dy dx, but the answer is going to turn out to be in terms not only of x, but also of y. Let's try to solve it. If we want to solve for dy dx, the first thing I want to do is get this 2x out of here and over here. To do that, I subtract 2x from both sides of the equation, and I have 2y times dy dx is equal to minus 2x. Now, to solve for dy dx, I have to divide by the coefficient of dy dx, namely 2y. Divide both sides of the equation by 2y, and I get dy dx is equal to minus, now when I divide by 2y, these 2's are going to cancel, so I'm going to get minus x divided by y. That's the derivative of y with respect to x in terms of x and y. Now here's a good opportunity for you to turn off your VCR, try to solve this equation for y explicitly in terms of x, take the derivatives by the methods you used before, and see that in fact you have the same result that I got over here. However, I will warn you that when you solve for y in terms of x, you're going to have to take a square root, and you're going to have to take plus or minus. So you'll actually have two possible functions to work with. Choose either one and verify that the derivative is correct. Now, I haven't quite finished the problem, though, because my problem was to find the slope of the tangent line at the point 3, 4, which means I have to take this derivative and evaluate it at the point where x is 3 and y is 4. That's easy enough. I'll just substitute 3, 4 for xy, and I get that the slope of the tangent line is minus 3 over 4, or minus 3/4. What's interesting about this result is that there is a well-known geometric theorem which says that the tangent line to a circle at any point is perpendicular to the radius of the circle at that point. Remember, this is a circle of radius 5 centered at the origin. So let's take a look over here. Here's a graph, circle of radius 5, centered at the origin, and we're going to be drawing the tangent line at the point with coordinates 3, 4. Here's 3, 4, is right about here, and the tangent line at this point has slope minus 3/4. So it looks something like this. This is the point 3, 4. If we take a look at the radius from the center of the circle over to this point, it looks like this. Now, what's the slope of that radius? Well, this is the point 3, 4. So this distance over here is 4, and this is 3, which means the slope of this radius is m equals y over x. Actually, change in y over change in x, but of course at the origin, y and x are 0. Y over x is 4/3, and we see that the slope of the radius is the negative reciprocal of the slope of the tangent line, as we just found it. 6b, we're asked to find the equation of the tangent line to the curve defined by the equation x cubed plus 4y squared equals 6xy plus 8 at the point with coordinates minus 2, 1. Now actually you should verify that the point minus 2, 1 really lies on the curve. That is, you should substitute x equals minus 2 and y equals 1 into this equation and see that the equation is true. I'll let you do that. I'm going to take the derivative of this expression so that I can find the slope of that tangent line. Now, the derivative I'm going to have to do implicitly. I wouldn't try to solve this equation for y in terms of x explicitly. Taking the derivative, we start with the first term. The derivative of x cubed is 3x squared plus the derivative of 4y squared. Now remember, y is some function of x, so I need that extended power rule, that chain rule, to find the derivative. The derivative of 4y squared is 8y times the derivative of y with respect to x, because y is a function of x. So this is times dy dx. This is equal to the derivative of the other side. Now on the other side, we start with 6xy. That's a product, and we need the product rule. Remember the product rule. It's the first factor, and let the first factor be 6x, times the derivative of the second factor, plus the second factor times the derivative of the first factor. So, first factor is 6x times the derivative of the second factor. Y is some function of x, so the derivative of y is dy dx plus the second factor, that's y, multiplied by the derivative of the first factor. The derivative of 6x is 6. Plus the derivative of 8. 8 is a constant. The derivative of the constant is 0. So we have this very complicated looking expression that relates x, y, and dy dx. Notice this y6. Normally we write 6y, but because of the order of the product rule, it came out backward, but it means the same thing. Now we want to know the value of dy dx. Should we solve for dy dx through all this algebra? Well, I hope not to. After all, we only want to know the slope of the tangent line at the specific point minus 2, 1. So I'm going to substitute x equal minus 2, y equals 1 into this equation and solve for dy dx at the particular point. Substituting minus 2 in here for x, I get minus 2 squared is plus 4. 3 times 4 is 12. Next, 8y times dy dx. Well, y is 1, so 8 times y is 8. So I have plus 8 times dy dx. And this is equal to, substituting here for x, minus 2. I have 6 times minus 2 is minus 12. That's times dy dx, plus y times 6. Y is 1. 1 times 6 is 6. And now you see I have a little linear algebraic equation involving dy dx and constants. And what I want to do is collect like terms on each side of the equal sign and solve for dy dx. Now I have an 8 dy dx here and a minus 12 dy dx here. So let me add 12 dy dx to both sides of the equation. That avoids some minus signs. But at the same time, I'm going to want to get all the constants over to this side. So I'm going to subtract 12 from both sides of the equation. I'll make that a little lower down. It's an extra step. And now we'll combine everything. The 12s cancel, of course. 8 and 12 times dy dx is 20 times dy dx. And that's equal to, here I have 6 minus 12 is minus 6. So I have 20 dy dx is minus 6. Divide through by 20 and get dy dx is equal to minus 6 over 20, which is the same thing as minus 3 over 10. That's the slope of the tangent line, and if I want to find the equation of that tangent line, I'm going to need the point-slope formula from way, way back at the beginning. Point-slope formula, I take y minus y1. What's y1? Well, the original point we had to work with was minus 2, 1. So y1 is 1. We have y minus 1 equals the slope, m, minus 3/10 times x minus x1. x1 is minus 2, so I have x minus minus 2, which is x plus 2. Question 6c. They don't come much harder than this one. We start out with a product, x squared times y cubed. That's equal to 6x over y, that's a quotient, plus x to the 4th. And we're asked to find the derivative of y with respect to x implicitly, which means we're going to have to use the product rule, the quotient rule, the power rule, every rule we know. And to save a little bit of writing, instead of using dy dx this time, let me write y prime for the derivative. So we start with the product, x squared times y cubed, and we get, by the product rule, the first factor, x squared, times the derivative of the second factor. The derivative of y cubed, using the chain rule, is 3y squared times y prime. That's the first half of the product rule. Plus the second factor, y cubed, times the derivative of x squared. And the derivative of x squared is easy. That's 2x. This is equal to, now we take the derivative of 6x divided by y. That's a quotient. And we have to use the quotient rule. Remember, y is a function of x. Taking the derivative, we get the denominator first, that's y, times the derivative of the numerator. The derivative of 6x is 6, minus 6x times the derivative of y. The derivative of y is y prime. The whole thing divided by the square of this denominator, and the square of y is y squared. Plus, finally an easy one, the derivative of x to the 4th is simply 4x cubed. Now, the algebra is actually harder than the calculus. We want to solve for y prime. This is a very cumbersome looking expression. I think the first thing we ought to do is multiply through the entire equation by y squared. That'll get rid of all the denominators, and then we'll be able to proceed in grouping terms. So let's try. Multiplying the entire equation by y squared, what do we have? Well, this first term, we have 3x squared y squared. We multiply by y squared, so we get 3x squared y to the fourth, and this is multiplying y prime, plus the next term we have 2x times y cubed. We multiply by y squared. That gives us 2x times y to the fifth. So we have 2x times y to the fifth power. That's the left-hand side. This equals, now, multiplying through by y squared just wipes out this denominator. So we're left with the numerator here, which is y times 6, which of course we'll write as 6y, minus 6x times y prime. And finally, when we multiply this term by y squared, we get 4x cubed times y squared. Now what we want to do is group together on one side of the equation all the terms that involve y prime, and everything else we want to group on the other side of the equation. So here we have 3x squared y to the fourth y prime, and over here we have a minus 6x y prime. So let's add 6x times y prime to both sides of the equation. And at the same time, as we do that, we're going to move this 2x y to the fifth term over to the right-hand side by subtracting 2x y to the fifth from both sides of the equation. Can we do that? Here we have 3x squared times y to the fourth times y prime plus 6x times y prime. These two terms drop out, equals 6y, these cancel out, plus 4x cubed times y squared minus 2x y to the fifth. Finally, on this side of the equation, we have two terms, both of which involving the factor y prime. We can factor the y prime. It's a common factor in both terms. And we have y prime times 3x squared y to the fourth plus 6x. And that's equal to, I'm just going to have to recopy this, 6y plus 4x cubed y squared minus 2x y to the fifth. One last step, and what is that? We have to divide the entire equation by the coefficient of y prime in order to solve for y prime. And the coefficient of y prime is this expression right here, 3x squared y to the fourth plus 6x. So we have here in the numerator 6y plus 4x cubed y squared minus 2x y to the fifth, the whole thing divided by 3x squared y to the fourth plus 6x. They say a picture is worth 1,000 words, and in mathematics, a picture means a graph. If we have a relationship between two variables x and y, and we can draw a graph of y versus x, then we know everything there is to know about the relationship. In problem 1, we have y equals x squared minus 4x plus 2. And we're asked first to find the critical points for this graph. Well, the first thing we have to know is, what is a critical point? A critical point is a point at which the derivative of the function either does not exist or is equal to 0. This function is a polynomial. For a polynomial, the derivative exists everywhere. Therefore, the critical points are only those places where the derivative is equal to 0. In order to find the critical points, we must first find the derivative. Y prime, the derivative of y, is equal to 2x minus 4. Y prime gives the derivative as a function of x for any value of x. We want to know the place where this derivative is equal to 0. So we set y prime equal to 0, and we have 0 is equal to 2x minus 4. Well, that's easy to solve. 2x equals 4, and x equals 2. So the critical value is x equals 2. The critical point on the curve is the point where x is equal to 2 and y is equal to whatever the corresponding value is on the curve. That we're going to have to calculate from our original equation for y in terms of x. That is this equation. So y is equal to x squared, that's 2 squared is 4, minus 4x is minus 8, plus 2. Or in other words, at this point, y is equal to minus 2, and we would say the critical point is 2 minus 2. There's only one critical point for this graph. In part B, we're asked to find those regions for which the function is increasing and those for which it's decreasing. Well, what do we know? The derivative of a function tells you the slope of the tangent line to the curve at any point. If the slope of the tangent line is positive, that means that as you go from left to right, you're going up. In other words, the function is increasing. The y values are getting greater. If the derivative, on the other hand, is negative, that means the slope is negative, which means the curve must be going down as you go from left to right. In other words, y is decreasing. So in order to tell where the function is increasing, where it's decreasing, we simply look at the derivative formula and see where that's positive and where it's negative. Now, our derivative formula in this case, we just found, is y prime equals 2x minus 4. We're going to factor a 2, and we have y prime is 2 times the quantity x minus 2. And now we want to know, where is this expression positive and where is it negative? We know it's 0 at x equal 2. That's what we found in part A. Well, look, 2 is a positive number. What about x minus 2? Well, the value of x minus 2 depends upon x. If x is larger than 2, which of course mathematically we write this way, if x greater than 2, then y prime is positive, because x minus 2 will be positive, 2 times that will be positive. So if x is greater than 2, then y prime is positive, and positive we write this way, greater than 0. That means positive. So if x is greater than 2, then y prime is greater than 0, which means y is increasing. Let's get that straight. It's when y prime is positive that y is increasing. So if x is greater than 2, y is increasing. On the other hand, x could be less than 2. Well, if x is less than 2, then x minus 2 is going to be negative. Is that right? If you take a number that's less than 2 and subtract 2 from it, the result is going to be negative. So if x is less than 2, then y prime is going to be negative. Why? Because x minus 2 is negative, and 2 times a negative number is still negative. So if x is less than 2, y prime is negative, and y is decreasing. In part C, we're asked to determine any relative maxima or relative minima for the curve. Now, for a polynomial, the only place you can find a relative maximum or minimum is a place where the derivative is equal to 0. That is a critical point. At such a point, the tangent line to the curve has 0 slope, meaning it's horizontal. The only possibility then for this curve is at x equals 2. Now, let's see. Is that a relative maximum or a relative minimum? Well, if you look at what we've just done, when x is greater than 2, y is increasing. That means if you go to the right of 2, the curve is going up. On the other hand, if x is less than 2, y is decreasing. That means coming from the left towards x equal 2. Let me give you a little picture here. If this is x equal 2, coming towards x equal 2 from the left, your curve must be going down. Coming the other way, that is going from 2 towards the right, x is greater than 2, y is going up. Well, there's only one possibility then. It's going down, it reaches a critical point where it has a horizontal tangent, and then it's got to go up. Therefore, we're forced to conclude that the point 2 minus 2 is a relative minimum for the curve, meaning when x equals 2, y reaches its lowest possible value in that vicinity, which is y equals minus 2. For this curve, it turns out that y equals minus 2 is, in fact, the absolute minimum value for y. Now, you recognize this curve actually from its equation as being a parabola. So let's take a look at the graph of that parabola and see how the information we've just found ties up with the graph. Here's the graph of the parabola that we've just been analyzing. You can see this critical point at x equals 2, y equals minus 2. That's the lowest point on the curve. To the left, you can see the curve is decreasing. The derivative is negative. Any tangent line you would draw here has negative slope. On the other side, the graph is increasing. Y is getting larger. Any tangent you would draw has positive slope. At the critical point, you can see that if we tried to draw a tangent line, it would be exactly horizontal. That is, it would have zero slope. That's how we found the point. As a second example, let's look at another polynomial, this time a fourth degree or quartic polynomial. Y equals x to the fourth minus 2x squared plus 3. And once again, the study guide says, follow the directions that we used in example 1. So part A is to find the critical points. Again, this is a polynomial. The critical points are found where the derivative is equal to 0. So let's find the derivative. Y prime is equal to 4x cubed. The derivative of minus 2x squared is minus 4x plus the derivative of 3, which is 0. So y prime is 4x cubed minus 4x. The critical points are found where this derivative is equal to 0. So let's set y prime equal to 0. And we have 4x cubed minus 4x is equal to 0. Now that's a cubic, and it's not easy to find the roots of a cubic, but this particular one we can factor very nicely. There's a common factor of 4x in both terms. So we factor 4x. Factoring 4x from 4x cubed leaves just x squared. Factoring 4x from minus 4x leaves minus 1, and that product has to equal 0. Now, once we've done that factoring, it's really easy to see x squared minus 1, we know that factors. That's a difference of squares, and we have 4x times x minus 1 times x plus 1. And now it's easy to see what the roots are, because when you have the product of three factors, the only possibilities that make the product 0 are that one of the three factors has to be 0. Well, 4x can only be 0 when x is equal to 0. X minus 1 is 0 only when x equals 1. And x plus 1 is equal to 0 only when x equals minus 1. So we have three critical numbers, x equals 0, x equals 1, and x equals minus 1. Now, we'd like to know the y values that correspond to those 3 points. And we go back up to our original equation for y, which is y equals x to the fourth minus 2x squared plus 3. And we start with x equals 0. This we can do in our heads pretty easily. If x is 0, then x to the fourth is 0. 2x squared is 0. So y has to equal simply 3. Our first critical point is 0, 3. Let's try the second one. We substitute x equal 1. Fortunately, 1 is easy to work with, so we can work that out also. 1 to the 4th is 1. Minus 2 times 1 squared, well, that's again 2 times 1. So this is 1 minus 2 plus 3. 1 minus 2 plus 3 is 2. Interestingly, when we substitute x equals minus 1 for the third point, you see we have x to the 4th and x squared. Both of those are going to give you plus 1 when you substitute minus 1 because it's an even power. So x to the 4th minus 1 to the 4th is 1. X squared minus 1 squared is 1. So again, we have 1 minus 2 plus 3, or in other words, y is equal to 2. So we have 3 critical points, and they are 0, 3, 1, 2, and minus 1, 2. Next, we're asked to find where this function is increasing and where it is decreasing. Now, this is going to be more difficult than the last problem because the first derivative is a more complicated expression. Remember, the first derivative here is y prime equals 4x cubed minus 4x. And we want to know where this is positive, because that will tell us where the function is increasing. And we want to know where it's negative, so that will tell us where the function is decreasing. Fortunately, down here, we factored this part. And I'm going to take advantage of the fact that I've already done that and say that y prime is equal to 4x times x minus 1 times x plus 1. Now, this is a tricky method that you probably learned in pre-calculus to tell where a product is positive and where it's negative. You have the product of 3 factors. If you want that product to be positive, then either all 3 factors have to be positive, or one of the factors has to be positive and the other 2 negative. Let me say that again. If I have 1 negative factor and 2 positive ones, then the product is going to be negative. So the only way I can get a positive result is if all 3 factors are positive, or if 2 are negative and 1 is positive. So what I'm going to do is ask, where do each of these factors change sign? Well, let's see. 4x changes sign at x equals 0. X minus 1 changes sign at x equals 1. And x plus 1 changes sign at x equal minus 1. Let me try to draw a little bit of a number line and show you what we have. This is minus 1. This is 0. This is plus 1. We have 3 factors there, 4x, x minus 1, and x plus 1. If you go to the left of minus 1, that is, if x is less than minus 1, then 4x is negative, x minus 1 is negative, because you take a number less than minus 1 and subtract 1 from it, it's certainly going to be negative, and x plus 1 will also be negative. So all 3 of these factors are going to be negative in this region. If you go from minus 1 to 0, then what happens? Well, the factor x plus 1 changes sign at x equals minus 1. So over here, x plus 1 will become positive, and it will stay positive from then on. On the other hand, 4x will still be negative over here, and x minus 1, well, again, we're looking at x to the left of 0. That is, x is negative. You subtract 1, it will still be negative. So x minus 1 is going to be negative here. Moving right along, to the right of 0, 4x becomes positive because x changes sign at 0, and it remains positive over here. X minus 1 remains negative until you get up to 1, and then it changes sign and becomes positive. Now let's look at the sign of y prime in each of these regions. In the first region, that is to the left of minus 1, we have the product of 3 negative numbers, so y prime is negative. Between x equals minus 1 and 0, we have the product of two negatives and a positive, so y prime is positive. Between 0 and 1, we have the product of two positives and a negative, so y prime is once again negative. And finally, to the right of 1, we have the product of three positive numbers, so y prime is positive. Now, what does this tell us about the function y? Well, it says the following. If x is to the left of minus 1, that means if x is less than minus 1, or if x is between 0 and 1, like this, x between 0 and 1, 0 less than x less than 1, then y prime is negative, and that means that y is decreasing. In the other two regions, that is between minus 1 and 0, if x is between minus 1 and 0, or if x is greater than 1, I'll write that 1 less than x, then y prime is greater than 0, and in those two regions, y is increasing. Now that's a lot of information to have about the relationship. But Part C asks us for one more piece of information, and that is, what are the relative maximum and relative minimum values of y? Well, let's see. Moving from left to right, along this graph from the information we have here, we have the following information. If x is less than minus 1, y is decreasing. That means it's going down. On the other hand, if x is between minus 1 and 0, it's increasing. That means as x gets near minus 1, first the function is decreasing, and then it's increasing. That means that at x equals minus 1, we must have a relative minimum value. We're coming down to minus from the left, and then we're going up to the right. So at x equals minus 1, where we calculated earlier that y was equal to 2, we have a relative minimum, which I'll abbreviate rel min. Moving along, we get towards 0. Now, to the left of 0, y prime is positive. The function is increasing. That means we're going up. On the other side, between 0 and 1, y prime is negative. Y is decreasing. So that means as we come towards x equals 0, first we're going up, then we're going down. That means we must have reached a relative maximum. And that would be at x equals 0, where y we already calculated was 3. And that's a relative maximum. And finally, we get over to x equals 1, our last critical point. To the left of x equals 1, that's x between 0 and 1, we see that y is decreasing. To the right of x equal 1, y is again increasing. So as we approach x equal 1, y first goes down and then comes up. It goes down and comes up. It must reach a relative minimum. And at x equals 1, where again we've already computed that y is equal to 2, we have a second relative minimum value for the function. Now, this is a graph you're probably not familiar with, but I'd like you to take a quick look at it. Here's the graph of y equals x to the fourth minus 2x squared plus 3. You can see to the left of minus 1, this graph is going down. That is, y is decreasing. It reaches the critical point at x equal minus 1, where y is equal to 2. You can see the horizontal tangent that would be there if you wanted it. Then it increases up to this point where x equals 0 and y equals 3. And that's our relative maximum. Notice the relative maximum is not the highest value of y that we ever get. We get higher values here and here. But for its immediate vicinity, this is the high point, a relative maximum. The function then decreases again between 0 and 1, reaching another relative minimum at x equals 1, where y is again equal to 2. Again, a horizontal tangent. And then it goes up again after we pass x equals 1. Well, problem 2 is a toughie, and I hope you've taken some time to look at it again carefully. I'm going to go on now to problem 3. Here we have a cubic, y equals x cubed plus 3x squared minus 9x minus 10. And the first part of the problem says, find those regions in which the curve is concave up and those regions in which it's concave down. Well, what does that mean? Concave up means roughly like this. The curve curves upward. Concave down means something like this, the curve going this way. How do we detect concavity? We look at the second derivative. When the second derivative is positive, the curve is concave up. When the second derivative is negative, the curve is concave down. So I'm going to have to take 2 derivatives of this function. That's not difficult. Y prime, the first derivative, is equal to 3x squared plus 6x minus 9. Second derivative, the derivative of the first derivative, y double prime, is simply 6x plus 6. And now in order to detect concavity, we have to check where is this second derivative positive and where is the second derivative negative. Well, a good idea would be to check where is the second derivative 0. And that's not hard to do at all. If we set y double prime equal to 0, we see that we have 6x plus 6 equals 0. That gives us 6x equals minus 6, or x equals minus 1. Well, if x equals minus 1 gives you the second derivative equal to 0, then clearly that must say something about how y double prime changes sign from positive to negative or negative to positive. Let's see. If x is less than minus 1, then what happens? Well, if x is less than minus 1, then 6x is going to be a number smaller than minus 6. And if you add 6 to that, you're going to get a negative result. So if x is less than minus 1, then y double prime will be negative, and the curve will be concave down. Of course, if x is greater than minus 1, that means x is something like minus a half or 0 or 1 or 2. If you take 6 times that, you're going to get a number that's larger than minus 6, and when you add 6 to it, the result will have to be positive. So if x is greater than minus 1, then y double prime is greater than 0, and the curve is concave up. What about the point where x equals minus 1? Well, where x equals minus 1, the curve changes concavity. That is, it goes from being concave down to being concave up. Such a point is called a point of inflection. So at x equals minus 1, we have a point of inflection. Since it's a point, we really should know its coordinates. So when x equals minus 1, I'd like to know the y-coordinate. Where am I going to get the y-coordinate from? I have to get the y-coordinate from the original equation, which gives the relationship between x and y. Here I have y equals x cubed plus 3x squared minus 9x minus 10. And if I want to know the value of y when x equals minus 1, I simply substitute minus 1 into this equation. Let's see if we can do that in our heads and put the answer right down here next to the x equal minus 1. We get y equals, well, if you substitute minus 1 here, you get minus 1 cubed. That's minus 1. Plus 3 times minus 1 squared. Minus 1 squared is plus 1. 3 times that is 3. Minus 9 times minus 1 is plus 9. And then we have minus 10. And if we add this up, this is what? Minus 1 plus 3 is 2, plus 9 is 11, minus 10 is 1. So the point of inflection is at minus 1, 1. Write that about here. Minus 1, 1 is a point of inflection. Part B of the problem says, sketch the curve showing all relative maximum and minimum points. Now, how are we going to find maximum and minimum points? Well, for that we have to step backward and look at the first derivative. The first derivative, set equal to 0 and solve for x, will tell you the critical values for the curve. And we know that maximum and minimum values of polynomials are found at critical points. So I have to go back to this formula, the first derivative formula, set this one equal to 0, and solve for x to try to find critical points. So I'm going to set y prime now equal to 0. Let me see. Y prime equals 0, and I have 3x squared plus 6x minus 9 equals 0. I can divide through by 3 and get x squared plus 2x minus 3 equals 0. That's a quadratic equation. I can factor x plus 3 times x minus 1 equals 0. And this gives me x equals minus 3 and x equals plus 1. These are the critical numbers and give us possible relative maximum or minimum values. Now let's think about this for a second. X equals minus 3. That's to the left of minus 1. That's to the left of the point of inflection. At x equals minus 3, this curve is concave down. Now, what does it mean? The curve is concave down, and you have a horizontal tangent. You have a place where the derivative, the first derivative, is equal to 0. That's a point of horizontal tangency. Let's take a look at that. If you have a point of horizontal tangency that's concave down, let's see, I have a little room over here, the curve has to look something like this. It's got to be concave down and have a horizontal tangent. Similarly, at x equals plus 1, you're in the region where x is greater than minus 1 and the curve is concave up. So at x equals plus 1, the curve has a horizontal tangent and it's concave up. That means the graph has to look something like this. It's got to be concave up and have a horizontal tangent. So the first case, x equals minus 3, concave down, horizontal tangent, that's got to be a relative maximum. Second case, concave up and a horizontal tangent, that's got to be a relative minimum. So at x equals minus 3, I'm going to have a relative maximum, and at x equals 1, we're going to have a relative minimum. Now, all I have to do is calculate the y values at those points. So, where do I get the y values? Again, I go back to the original equation that I had, and I have to compute the value at x equal minus 3 and the value at x equal 1. Let me try that right over here. At x equal minus 3, we have y equals minus 3 cubed is minus 27, plus 3 times minus 3 squared. Minus 3 squared is 9. 3 times 9 is 27. Minus 9 times minus 3 is plus 27, minus 10. And that adds up to what? Let's see. Minus 27 plus 27, that drops out. So I have 27 minus 10 is 17. So let's see. What did I say? That's x equal minus 3. Y equals, what did I just say? 17? Minus 3, 17, and we had decided that that's going to be a relative max. Can I erase again? Let me get rid of this, and we'll substitute into this formula now the other critical number, x equals 1. Substituting x equal 1, we get 1 cubed is 1, plus 3 times 1 squared is 3, minus 9 times 1 is 9, minus 9, minus another 10. Let's see, what's that? 4 minus 9 is minus 5, minus 10 is minus 15. So that was what? X equals 1, right? At x equals 1, y equals minus 15, and that's a relative minimum. Now we have a relative maximum, a relative minimum, and don't forget that point of inflection that we got earlier. Now let's move over to a little set of axes and see what the graph actually looks like. Here are the axes. Now we have a relative maximum point at x equal minus 3, y equals 17. Let's say minus 3 is about over here. I'll have to distort the y scale a little bit because the y numbers are getting pretty large. So let's say y equals 17 is about here. That means we've got a point over here on the graph that's a relative maximum. That means at this point the curve has got to look something like that. If we move over to the relative minimum, that's at the point x equal 1, y equals minus 15. So x equals 1 would be about here, and minus 15 would be down here somewhere, not quite as far down as this one is up. And we've got a point down here, and here we've got a relative minimum, which means over here the curve has to look something like this. Finally, we have that point of inflection, the place where the curve changes concavity, and that's at x equal minus 1, y equal plus 1, which on this scale probably puts it about here. And that's the point of inflection. Now, what does the rest of the graph look like? Well, clearly, what doesn't happen is as important as what does happen. There are no other places where this graph can change direction. That is, over here, it's got to go up to that maximum. It can never turn around, or we would have found a place where it turned. We would have found another critical point. It also has to remain concave down. Otherwise, we would have found another inflection point. So over here, the curve must look like that. Now, it has to remain concave down until we reach the inflection point. So it goes down like this. At this point, it changes concavity and becomes concave up, leading into that minimum point. So it goes something like that. And finally, after you pass the minimum point, the curve has to increase away from it, remaining now concave up because there are no other points of inflection. So the graph goes like this. And we have this very nice up, down, up pattern, which is very typical of graphs of cubics. Let me point out that my graph has to be off by a little bit because if you look at the original formula, when you substitute x equals 0 into the original formula, you see that y is going to be minus 10. And clearly this graph does not cross the axis at minus 10 the way I've drawn it, but this is a freehand sketch, and if you took a piece of graph paper, I'm sure you could do a better job. Now, let me see if I can summarize the methodology that you're going to use to draw the graphs of particularly polynomial curves. First, you're really going to look for maximum and minimum. And to find maximum and minimum, you look for critical points by setting f prime of x equal to 0 and solving for x. Next, you take the x values you find, substitute into f double prime of x. If f double prime of x is greater than 0, then you have a minimum value. If f double prime x is less than 0, then you have a maximum value. But if f double prime of x equals 0, then you're going to have to check for maximum and minimum by looking at the slopes of the curve to the right and left of the critical point. Finally, step 3, to find points of inflection, you set f double prime of x equal to 0, solve for x, and then check for change of concavity to the left and right of those points. Let's try to apply the methods we just summarized to problem 4. Problem 4, we have y equals 4x cubed minus x to the 4th. And we're going to try to find relative maximum, relative minimum, and points of inflection, and get a graph of this curve. In order to do that, we're going to need two derivatives. So y prime is equal to 12x squared minus 4x cubed. And y double prime, the derivative of the first derivative, is 24x minus 12x squared. Oops. Okay. We want to check first for relative maximum and relative minimum. To do that, we have to look for the critical points. Critical points are places where the first derivative is equal to 0. So let's set y prime equal to 0 and try to solve for x. Here's y prime. It's 12x squared minus 4x cubed, and that has to equal 0. Now, to solve this, we're going to have to factor it. You can see that there's a common factor, 4x squared, in both terms. So we factor 4x squared. We get 4x squared times, factoring from 12x squared, we're left with a 3. And factoring from 4x cubed, we're left with x. So we have 4x squared times 3 minus x equals 0. We have two factors whose product is 0. The only way we can get this to happen is if at least one of the two factors is 0. There's only two possibilities. The only way 4x squared can equal 0 is if x equals 0. And the other possibility is that 3 minus x equals 0. And the only way that can happen is if x is equal to 3. So we have two possible critical values, x equals 0, x equals 3, and we'd like to know whether those points are going to give us relative maximum or relative minimum. Now, what did we say in the summary? Take these values and substitute into the second derivative and see whether the second derivative is positive or negative. So we look at the second derivative, which is 24x minus 12x squared, and we substitute first x equals 0. If we put in x equals 0 into the second derivative, we get y double prime is equal to, well, it's 24x minus 12x squared. If you substitute x equals 0, you just get 0. So immediately, the first time we try to do it, it turns out that the second derivative is equal to 0, and we don't know whether we have a maximum or a minimum. But let's leave that for the time being, simply remembering that there's another possibility here that we've discovered purely by accident, and that is that if the second derivative is 0, we have a possible point of inflection. So we have to consider all these possibilities. It could be a maximum, it could be a minimum, or it could simply be a point where the tangent line is horizontal. Remember, the first derivative is 0. And we also have a point of inflection at the same place. So let me give us some questions that we have to work on. Max or min, or inflection. All are possible. In the meantime, let's move on to x equals 3. Remember what we're doing. We're checking whether we're getting a maximum or a minimum at this point. We want to know if it's a maximum or minimum. We're going to try this second derivative test. Substitute x equals 3 into y double prime and see whether we get a positive or a negative result. So let's see. At x equals 3, we have y double prime is equal to, let's see, 24 times 3 is 72 minus 12 times 3 squared. 3 squared is 9. 12 times 9 is 108. So we have 72 minus 108. And I guess that number is minus 36, but it's minus. That's what really counts. I don't really have to know exactly what the number is. I simply want to know that this is negative. Now, what does that tell us? At x equals 3, the second derivative is negative. It's a critical point, so the first derivative is 0, meaning we have a horizontal tangent and it's concave down, and therefore at x equals 3, we have a relative maximum. Of course, we have to know the y value as well, and to get the y value, we have to substitute x equals 3 back into that original equation which gave us y in terms of x. So let's substitute x equals 3 into that original equation and see what we get for y. That's going to be our relative maximum. Okay? X equals 3, we get y equals 4 times 3 cubed, that's 4 times 27, minus 3 to the 4th. 3 cubed is 27. 4 times 27 is 108. Minus 3 to the fourth. What's 3 to the fourth? 81. 108 minus 81 is 27. So we have a relative maximum, and that relative maximum is 327. How are we doing? Well, we've identified a relative maximum, and we've identified one possible point of inflection by luck, and we still have to do something with that point, x equals 0, where incidentally, it's not hard to see y is also equal to 0, because the original equation is y equals 4x cubed minus x to the fourth, and if we substitute x equals 0, we get 0. So let me write that down for the moment. The questionable point is 0, 0, and we're going to hold that while we look for any other possible points of inflection. Because why? When we want to look for points of inflection, we look for places where the second derivative is 0, and then we have to check on both sides of those points to see whether or not the concavity has changed. Let's take a look at that second derivative now. Second derivative, y double prime equals 24x minus 12x squared. Y double prime equals 24x minus, I always want to leave that x out, 24x minus 12x squared. Let's factor that. We have y double prime equals, how can I factor this? I have a common factor of 12x. So I have 12x times 2 minus x. And now I can see in this form that the places where y double prime could be 0 is at x equals 0, which we already found, or at x equal 2. All right? So y double prime equals 0 at x equals 0 or x equal 2. Are either of these points of inflection? Well, again, keep looking at this. If x is less than 0, what happens? 12x will be negative. 2 minus a negative number is positive. So we have a negative times a positive. That's negative, right? So if x is less than 0, y double prime is negative, and the curve is concave down. Maybe I should write that down. If x is less than 0, we have concave down. Well, what about around x equal 2? Well, what we have to do is look between 0 and 2, and then to the right of 2. Between 0 and 2, if x is any number between 0 and 2, try 1, for example. If x is any number between 0 and 2, 12x is positive. 2 minus x, say if x were 1, that would be 2 minus 1. That's also positive. This product is positive. That means y double prime is positive. The curve is concave up. So if x is between 0 and 2, the curve is concave up. Now wait a minute. That means we've actually solved our first little problem, which is the point 0, 0 a point of inflection, or is it not? Answer, it is. To the left, it's concave down. To the right, it's concave up. That means we have a point of inflection at 0, 0. But let me go on. If x is greater than 2, then what happens? If x is greater than 2, 12x is positive. 2 minus x becomes negative. Second derivative becomes negative, and the curve becomes concave down again, which means at x equal 2, we have a point of inflection, and let's get the y value at that point. To get the y value at x equal 2, we have to go way back to that original equation for y and substitute x equal 2. Substitute x equal 2 into y equals 4x cubed minus x to the fourth. Can I do that in my head? Let's see. If I substitute x equal 2 here, I have 4 times 2 cubed. 4 times 2 cubed is 8, times 4 is 32. Is that right? 4 times 2 cubed is 32. Minus 2 to the fourth. What's 2 to the fourth? 2 to the fourth is 16. So I have 32 minus 16. In other words, at x equal 2, y is equal to 16, and that's a point of inflection. You Think you can remember all that? Well, let's put it on the graph and see what it looks like. What have we found so far? We found a relative maximum at the point 327. Let's go over here to the axes. X equals 3, we'll put, say, over here somewhere. Y equal 27 is going to be way up off my axis, so I'm just going to estimate its height, say here. And over here we have a relative maximum. Now we have two other points of interest. One I haven't even written down for you yet. That was the original point that gave us the big problem where x equals 0, and that's the point 0, 0. And we had decided that 0, 0 is going to be a point of inflection, and that's right over here, the origin. We have a point of inflection, but don't forget, it's a point of inflection where there's also a horizontal tangent. That means the curve has to be something like this, going through this point. It's concave down on this side, and it's concave up on this side. That means over here, this graph has got to look something like that. Finally, we have one more point, and that point is x equals 2, y equals 16, and that would be up here, roughly. And that's going to be the other point of inflection. So let's see what happens. At the top here, this 327 is a relative maximum, so the graph looks like this. It remains over here, concave up till it reaches that point of inflection at 216. Then it becomes concave down, goes through the maximum, and continues on downward like that. On the left-hand side, it was concave down, coming through the origin, and it remains like that. Now you can see what happens at the point of inflection. We have this curve. It's increasing, but it starts to slow down. It's increasing at a lower rate. The tangent lines are becoming less steep. After it passes through the inflection, the steepness increases, so we're increasing at a greater rate than we were before. Similarly, at this inflection point, we start to reverse the process. We're increasing at a slower rate until finally we stop increasing altogether and then start downward. Now we're going to get into some of the really interesting problems in the calculus. You may wonder what I'm holding in my hand. Well, this is a model for problem 1 in part 6. Problem 1 says we're going to take a piece of cardboard, which is 12 inches by 12 inches, cut a square out of each corner, as we've done here, and then we can fold up the sides and form a cardboard box. All we need now, you see, is 4 pieces of cellophane tape along the edges, and we've got a box that we can store something in. But the problem doesn't say just form a cardboard box. It says form the cardboard box of maximum volume. Well, what does that mean? That means I want the cardboard box that will hold the greatest amount of material using just this square of cardboard. Why anybody would want to make a box this way is another question, but let's just assume that mathematicians aren't very well paid and we use whatever materials we have at hand. So what I've done here is I've drawn a diagram of that piece of cardboard, and you can see that I can form this box by folding up each of these 4 flaps that are formed by cutting out the squares. Of course, they have to be squares. That is, this distance has to equal this distance, so that when I fold it up, they'll match. Well, how big should that distance be? That's the question. So let's label that distance x. That distance is also x. That one, that one, that one, that one, that one, and that one. So now we have our 4 squares, each one distance x by x. Now the question is, how big is the box? That is, how big is the volume of the box? Well, the volume of a rectangular solid, the volume of a box, is given by the length, L, times the width, W, times the height, H. Well, what kind of box are we going to get? When we fold this thing up, the base of the box will look like this. And the base of this box is going to be this distance by this distance. What is this distance? Well, the entire side, you can see over here, the entire side is length 12. We cut out a piece of length x here and a piece of length x here, which means this piece left in the middle is going to be of length 12 minus 2x. Is that right? 12 minus 2x. X cut off from each end. So this is 12 minus 2x. Of course, this length is going to be the same because originally this was 12, and again we cut x and x off. So we have 12 minus 2x. When I fold it up, this is going to be the base of the box. So the length of the box will be 12 minus 2x. The width of the box will be 12 minus 2x. And all I need to know is the height of the box. How high is the box? Well, it's going to be the thickness of this flap. And the thickness of this flap is x. So I have this expression now. The volume is equal to 12 minus 2x by 12 minus 2x by x. So I have the volume of the box as a function of x. And what I want to do is find the value of x, which will make the functional value, the value of v, the largest possible. In order to do that, I'm going to now use the calculus, because we know that one good place to look for the maximum value of something is at a critical point, a place where the derivative of the function is equal to 0. Before I take the derivative, I'm going to multiply this out and get a polynomial. So 12 minus 2x by 12 minus 2x, 12 by 12 is 144. Minus 2x times 12 is minus 24x. Minus another 24x is minus 48x. Plus, right, minus 2x times minus 2x is plus 4x squared. The whole thing multiplied by x. One more step, and I get the volume is equal to 144x minus 48x squared plus 4x cubed. This is the volume as a function of x. If I wanted to, I could start substituting values of x and see what the possible values of v are. But I'm not going to do that. I'm going to go directly for the critical point, the place where the volume is maximum. In order to do that, I want to take the derivative of v with respect to x. The derivative of v with respect to x is dv dx is equal to the derivative of 144x is 144. The derivative of minus 48x squared is minus 96x. And finally, the derivative of 4x cubed is 12x squared. In order to find the critical point, the place where the volume is maximum, I'm going to set dv dx equal to 0 and solve for x. I put dv dx equal to 0, and now I recopy this right-hand side. Let me write it in the usual way we write polynomials, with the highest power of x first. So this becomes 12x squared minus 96x plus 144 equals 0. That's a quadratic equation. I have to solve it for x. First thing I'm going to do is divide through by the common factor 12 that occurs in every term. Dividing by 12, I get x squared minus 96 divided by 12 is 8. That's 8x plus 144 divided by 12 is 12. And that equals 0. Now, how do you solve a quadratic equation? Well, you could use the quadratic formula, but if you're lucky, you'll be able to factor this expression. Can you see what the factors are? We need two numbers whose product is 12 and whose sum is minus 8. And the easiest thing I can think of is x minus 6 times x minus 2. And you can check that. That's x squared minus 6x minus 2x is minus 8x plus 12. When you have a quadratic equation with the left-hand side factored like this, you know that the root can either be x equals 6, that makes this factor 0, or x equals 2. one of these two numbers is going to give us the maximum volume for the box. The question is, which one? Well, for that, we're going to have to go back and take another look at the diagram. If we go back to the diagram, we remember that x is the length of the square that was cut out of the corner. Well, if x is equal to 6, and the whole side is only 12 inches long, if we have 12 minus 2x, that's 12 minus 2 times 6, that's 0. What we've done is we've cut away the entire piece of cardboard, and there is no box at all. That can't possibly be the answer. Therefore, the correct answer has to be the other possible value of x, and that value is x equal 2. So substituting x equal 2 into this equation will give you the volume of the box that is maximum. In problem 2, we have a farmer who wants to make an animal pen, but he has a limited amount of fencing. In particular, the problem says he has 200 feet of fencing. Of course, you must understand that that means 200 running feet of fencing. That is, we don't care how high the fence is. So that pictorially, what we have is this pen, which is really composed of two parts. Fence down the middle, so we can keep one type of animal on one side of the fence and the other type of animal on the other side of the fence. If we call the length of this side y, then of course this distance is also y, and this distance is y. If we call this length x, then this distance is also x, because it's understood that the centerpiece divides the pen into two equal parts. And the problem says, find the dimensions of the pen that will give you maximum possible area. That is, with a limited amount of fencing, we want to have the area available to the animals to be as large as possible. Well, what do I mean by large in this case? In this case, large means maximum area for the entire pen. Well, the area of this pen is what? The area of a rectangle is the length times the width. The length of this pen is 2x. X here, x here. So the length is 2x, and the width is y, and the area is 2x times y. Now, this is a problem we haven't encountered before. A is not a function just of the variable x. It's a function of two variables, x and y. But you see, we have an extra condition on x and y that we haven't used yet. And that extra condition is that the total length of fencing that we're going to use must total 200 feet. Now, let's see. How much fencing do we have? Y here, another y here, another y here. That's 3y. Then we have distance x here, 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 and here. So that's 4x. So 3y plus 4x has to equal 200. Now you see the area is a function of two variables, x and y, but we have another equation that relates x and y. So we can solve this equation for y in terms of x, substitute it into the other equation, and then we'll have area as a function of one variable. Once we have the area as a function of one variable, we can use the calculus to solve the problem. Are you with me? To solve this for y in terms of x, first we'll bring the 4x over to the other side of the equation. That is, we'll subtract 4x from both sides, and we get 3y is equal to 200 minus 4x. Next, we divide by 3, and y is equal to 200 over 3 minus 4 over 3 times x. And now you see that I have y in terms of x, and I can get rid of the y in this original equation by substituting for y what it's equal to, 200 over 3 minus 4/3 times x. Let's do that now. The area is equal to 2x times 200 over 3 minus 4/3 times x. Now we have the area as a function of one variable, and the problem really is easy. It's downhill all the way. We multiply out, and we get the area is 400 over 3 times x. Is that right? 2x times 200 over 3 is 400 over 3 times x. And multiplying here, we get minus 2 times 4 is 8. This becomes x squared over 3. So we have 400 over 3 times x minus 8 over 3 times x squared. The area is a function of a single variable. We're going to, again, look for the critical point. The critical point where the derivative is equal to 0. We take the derivative. Let me call it a prime to save some writing. A prime is equal to 400 over 3. That's a constant times x. The derivative is just a constant. Minus the derivative of 8/3 x squared. We multiply by 2. Get 16 over 3 times x. Here's the derivative. The critical point is where the derivative is equal to 0. So we set a prime equal to 0. And this gives us, on the right-hand side, 400 over 3 minus 16 over 3 times x equals 0. We're going to solve this equation for x. First, multiply by 3 to get rid of the denominator, and we have 400 minus 16x equals 0. Bring the 16x over to the right-hand side, and we get 400 equals 16x. Finally, divide by 16, and you get x is equal to 400 divided by 16, which we all know is 25. Are we done? Well, not quite. You see, we know that x is 25, but we also want to know y. To get y, we have to go way back here to this equation that I boxed in before. Y is equal to 200 over 3 minus 4/3 x, and we have to substitute x equals 25 into this equation. Shall we do that? Substituting x equals 25, we get y equals 200 over 3 minus 4/3 times 25. Can I do that one in my head? 4 times 25 is 100, so this is 100 over 3. I have 200 over 3 minus 100 over 3. That's simply 100 over 3, or 33 1/3 feet. Am I really done? Again, the problem said find the dimensions of the pen. What are the dimensions of the pen? Go back to the diagram. The pen is actually y this way, but it's 2x this way. Okay? Y we've identified. Y is 33 1/3 feet. X is 25 feet. Therefore, this dimension, all in all, is 2x is 50 feet. So the farmer should make his pen 50 feet on a side and 33 1/3 feet for each of the fences going in this direction. Problem 3 is a problem in microeconomics. Economists always seem to work with widget manufacturers. Here we have a monopolist who manufactures widgets, and he finds that the demand equation for his product is 20x plus p equals 800, where x is the number of widgets that will be sold at price per widget p. In addition, he knows that the cost of producing widgets, c of x, that is a function of the number of widgets he produces, is 40x plus 2. And the problem is to find the widget production that will maximize his profits. Now, what are profits? Profits is revenue minus cost. So the first thing we must know is what his revenue is going to be. And moreover, we want to know what his revenue will be as a function of the number of widgets he sells, because his cost is a function of the number of widgets he sells. So what we're going to do is take this demand equation and find out what P is, that is the price per widget, in terms of X, the number of widgets. This gives us, solving this for P, we simply bring the 20x over to the other side of the equation by subtraction, and we get P is equal to 800 minus 20x. Now, what is revenue? Revenue is the number of items you sell times the price per item. That is, the amount of money that comes in is whatever you pay for an item times the number of items. So to get the revenue R is equal to P, the price per item, times X, the number of items. Therefore, the revenue is equal to, well, P, you see, is 800 minus 20x. So the revenue is really a function only of x. It looks like it's a function of P and x, but P depends on x. So the revenue is 800 minus 20x, the whole thing, times x. Notice I've substituted for P what its equivalent was in terms of x. Therefore, the revenue is equal to 800x minus 20x squared. But we're not interested in maximizing revenue. We're interested in maximizing profits. Profit is the difference between revenue and cost. So what we're going to do is take the revenue, R, and subtract from it the cost, C, and get the profit as a function of x. Now I need a symbol for profit. I would love to use P, but I'm using P for price. So let's take some other neutral letter. Maybe we'll choose S for profit. Why S? Because it looks like a dollar sign. And the profit, S, is equal to the revenue minus the cost. Okay? Now, what I have to do is substitute into this expression, S equals R minus C, what R is in terms of x, and what C is in terms of x, and I'm going to do that right over here. I have S is equal to, R was 800x minus 20x squared minus C, and C was 40x plus 2. Now I'm going to remove the parentheses, combine like terms, and get a single expression for profit. S is equal to 800x minus 20x squared minus 40x minus 2. Combining the like terms, 800x minus 40x, we have S is equal to 760x minus 20x squared minus 2. And now to find the maximum profit, all I have to do is find the derivative of the profit and get the critical point by setting the derivative equal to 0. So S prime is equal to the derivative of 760x is 760 minus the derivative of 20x squared is 40x. The derivative of minus 2 is again 0. And we're left with this very simple expression, S prime equals 760 minus 40x. We set S prime equal to 0. And we have 760 minus 40x equals 0. Add 40x to both sides. Get 760 equals 40x. And divide by 40 and get x equals 760 divided by 40, which is the same thing as 76 divided by 4, which is 19. So x is equal to 19. Now in a problem like this, you might be asked to find the price when x is equal to 19, the profit when x is equal to 19, the revenue, the cost, any of these things. They can all be obtained by substituting x equal 19 back into the original equations. Problem 4 deals with projectile motion under gravity. Now this is one thing you're supposed to know. You're supposed to know from your textbook that when a particle moves under gravity, the equation of motion is S equals minus 16 t squared plus v sub 0 times t plus s sub 0, where s, of course, is the position of the particle at any time t. V sub 0 is the initial velocity of the particle, and s sub 0 is the initial position. Now, where is the position measured from? That's really arbitrary, but we're going to assume that position is measured from the ground as 0. So the ground is 0, which means initially this particle begins at 384 for S0. That is, it starts on the top of a building 384 feet high. So S0 is 384. The initial velocity is given to be 160 feet per second in the upward direction. That means that V sub 0 is plus 160 feet per second. That means the equation of motion, the location of the particle at any time t, is equal to minus 16t squared plus 160t plus 384. Now let's see what the question asks. The first part of the question, part A, says find the highest point that the particle or projectile reaches. Well, what does it mean, the highest point? Let's see. If we look at this little diagram, the projectile over here is going upward. It reaches its highest point, and then it goes downward. Well, when it's going upward, it must have a positive velocity. When it's going downward, it must have a negative velocity. Hence, at the highest point, the velocity is equal to 0. So what we want to do is look at the velocity of this particle. Now, what's the relationship between the position and the velocity? Well, that's very easy. The velocity at any time is the rate of change of position, and the rate of change is the derivative. So the velocity is what we would call ds dt, or the derivative of the position. So the velocity at any time is ds dt, and that's equal to, directly from this equation, minus 32t plus 160. We want to know where this velocity is equal to 0. Well, let's see. If we put the velocity equal to 0, we get minus 32t plus 160 is equal to 0. Solving for t, that's 32t is equal to 160, and dividing by 32, we get t is equal to 5. What do we have? At t equals 5 seconds, the velocity of the particle is 0. That means at t equals 5 seconds, the particle has reached its highest point. But we want to know what the highest point is. That means we want to know what s is when t is equal to 5. So we go to the original equation for s, which is right over here, and we substitute in it t equal 5. So at t equal 5, s is equal to minus 16 times 5 squared plus 160 times 5 plus 384. Now let's see how good my arithmetic is. 5 squared is 25. 16 times 25 is 400. So this is minus 400 plus 5 times 160 is 800 plus 384. Minus 400 plus 800 is 400 plus 384 is 784. So the maximum height is equal to 784 feet. That's 784 feet above the ground. The particle actually rose 400 feet above the height of the building where it started. The second part of the problem says, find the velocity of the particle when it hits the ground. Now that's already a multi-step process. In order to find the velocity when it hits the ground, we first have to know when it hits the ground. Well, when does it hit the ground? It hits the ground when s is equal to 0. That is, when its position is 0. In order to solve for that time, we have to take the equation for s in terms of t, set it equal to 0, and solve for t. Let me recopy that equation right over here. We have s is minus 16t squared plus 160t plus 384, and that has to equal 0. This is a quadratic equation. In order to solve it, the first thing I'm going to do is divide through by minus 16, which divides into all of these coefficients. I get t squared. 160 divided by minus 16 gives you minus 10t. And 384 divided by minus 16, well, I know it's minus. How many times does 16 go into 384? It looks to me like 24 times. So we have t squared minus 10t minus 24 equals 0. And we're going to solve this quadratic equation by factoring. The factors of 24, whose difference is 10, are 12 and 2. So we have t minus 12 times t plus 2 equals 0. And that gives us two solutions, t equals 12 or t equals minus 2. Well, minus 2 can't be the right answer. That would be the particle hit the ground before we threw it. So it's got to be that it hits the ground at time t equals 12. Are we done? No, the question says find the velocity at that time. That means we want to take t equal 12 and substitute that into the equation, not for position, but for velocity. The equation for velocity we had at the very beginning of Part A. We have the velocity is equal to minus 32t plus 160. And we want to substitute in there t equal 12. So the velocity is equal to minus 32 times 12 plus 160. The velocity is equal to, what's minus 32 times 12? 384 minus 384 plus 160. That gives us minus 224 feet per second. And of course, it's minus because when it hits the ground, the particle is moving in the downward or negative direction. Problem 5 is a related rates problem. In fact, problem 5 is about the easiest type of related rates problem that you're possibly ever going to encounter. In this problem, we're told we have a spherical balloon being pumped full of helium. We're told the rate at which the helium is being pumped into the balloon is 100 cubic centimeters per second. We're asked to find the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. Now, the only thing you really have to know to do this problem is you have to know the formula for the volume of a sphere in terms of its radius. There you have two choices. Either you remember it or you look it up somewhere. The formula is V equals 4/3 pi times r cubed, where r is the radius of the sphere and v is the volume of the sphere. Now you must remember that since helium is being pumped into the balloon, the volume is changing with time. Therefore, the volume is a function of time. The radius is increasing also with time. So the radius is a function of time. Hence, if we take the derivative of this equation with respect to time, we'll get a relationship between the rate of change of volume with time, that is dv dt, and the rate of change of the radius with time, that is dr dt. So we take the derivative with respect to time. The derivative of v is dv dt. And that's equal to, now, 4/3 is a constant, pi is a constant. So the derivative of 4/3 pi r cubed is simply 4/3 pi times the derivative of r cubed. But you have to remember that the derivative of r cubed is being taken with respect to time. R is a function of time, and we're going to use the chain rule. When we do that, we get 4/3 pi times 3. The 3's cancel. And we get 4 pi times r squared. Now, don't forget that chain rule. R is a function of time, so the derivative is 4 pi r squared times dr dt. Now we have a relationship between the rate of change of volume, the radius r, and the rate of change of r, dr dt. We know that dv dt is given to be 100. The radius, well, they're a little sneaky here. We're told that the diameter is 20 centimeters. The diameter is twice the radius. So since the diameter is 20 centimeters, the radius is 10 centimeters. That's all the information we really need because we have dv dt, we have r, 4 pi is a constant, and we only have to find dr dt. So let's substitute the information we have into the equation, and we have 100 is equal to 4 pi times r squared. R is 10, so r squared is 100, times dr dt. To solve for dr dt, we just divide through by this coefficient. The coefficient is 4 pi times 100, but that's no problem. That's simply 400 times pi. And we divide that into 100 and get dr dt is equal to 1 over 4 pi. 1 over 4 pi what? Well, the volume is in cubic centimeters. The rate of change is cubic centimeters per second. Therefore, r must be in centimeters, and this is centimeters per second. So the rate of change is actually 1 over 4 pi centimeters per second. Notice that this is a positive number because that radius is increasing as we add helium to the balloon. Problem 6 is a very clever sounding problem. We have a burglar fleeing in a car heading due east on Main Street. He's going 45 miles per hour, which works out to be 66 feet per second. We'll write that down in a second. Try to remember it. A police car chasing him is going due south on 5th Avenue, and he's going 60 miles an hour, which is 88 feet per second. The question asks you to find the rate of change of the distance between the policeman and the burglar at a specific point in time. Now, in order to do this problem, we first have to put some kind of coordinates on our diagram. Due east, it makes sense to call the x direction. Due south, going this way, would really be the negative y direction. So let's make y go this way. And we'll let the location of the suspect car be, say, over here at some point, which is distance x from the center of the intersection. The location of the police car will let be at some distance y from the center of the intersection. And the distance between the suspect car and the police car is this distance, this diagonal distance, which I'll call z. Now you can see that at any time, x, y, and z are related by the fact that they form a right triangle. And we have a relationship between the sides of a right triangle and the hypotenuse, known as the Pythagorean theorem, which is probably the one geometric theorem that everyone remembers. And this theorem says that the square of this distance plus the square of this distance is equal to the square of this one. Or in letters, x squared plus y squared equals z squared. Now again, remember, X is changing with time because the burglar's car is going in this direction. Y is changing with time because the police car is going in this direction. And Z is changing with time because X and Y are changing. We want to know the rate at which Z is changing. Let's see what we do know. We know the rate at which X is changing. The burglar is going 66 feet per second. So dx dt, the rate of change, is 66. Notice, plus 66, because the burglar is going this way, which means X is getting bigger as time goes on. dy dt is the rate at which the policeman's car is moving. The policeman's car is moving 88 feet per second, but it's moving 88 feet per second in the negative direction. So dy dt is minus 88. What else do we know? Well, we're told that at a particular time, the burglar is 300 feet from the intersection, and the policeman is 400 feet from the intersection. At that time, X is equal to 300, Y is equal to 400, and of course you all recognize that we have a 3, 4, 5 right triangle, so that Z is going to be 500 feet per second. Now let's look at this. We know dx dt, we know dy dt, we know x, we know y, we know z. What do we want to know? We want to know dz dt. How are we going to find it? Well, we're going to take this relationship between x, y, and z, find its derivative with respect to time, and then substitute the information. Remember, x is a function of time, y is a function of time, and z is a function of time. We take the derivative with respect to time. We get 2x times dx dt by the chain rule plus 2y times dy dt is equal to the derivative of z squared with respect to t, 2z times dz dt. Shall we put in some information? Well, first let's divide by 2. That might make things easier. And now let's substitute. X is 300, so we have 300 times dx dt is 66 plus y is 400, dy dt is minus 88, and that has to equal z times dz dt. Well, z is 500, and dz dt is what we want to find. Here we go. I'm going to test my arithmetic again. 300, 400, 500, that means I can certainly divide the entire equation by 100 and save myself some writing. So let's do that. Divide by 100, and now we'll do the multiplication. 3 times 66 is 198. 4 times minus 88 is minus 352, I think. That's equal to 5 times dz dt. Now let's see. 198 minus 352 is minus 154 equals 5 times dz dt. And finally, we divide by 5, and we get dz dt is equal to 154 divided by 5 is 30.8. So that's minus 30.8. And what is that? Feet per second. Let me recopy that. dz dt is minus 30.8 feet per second. Notice, it's minus 30.8 feet per second. That means z is getting smaller as time passes, which actually means the distance between the burglar and the policeman is getting smaller as time passes. Problem 7. We have a conical reservoir full of water with water running out of it. We're told the water is running out of the reservoir at the rate of 12 pi cubic feet per minute. We're asked to find the rate at which the height of the water or the depth of the water in the conical reservoir is changing at a particular time. Now, let's take a look at the conical reservoir. This is a cone which represents our reservoir. Here's a little cross-section of the cone which we're going to have to use, and let's see what we're told. The radius of the top, this distance, is 4 feet. The height, or the entire depth of this cone from top to bottom, is 12 feet. So this distance is 4, this distance is 12. Now, at any time that we walk over, there's a certain amount of water in the cone, in the conical reservoir. Let's say the water level looks something like that. So that at some time t, or at any time t, the depth of the water in the cone is some value h, and the radius of this piece is some value r. Now, the volume of the water in the cone is itself in the shape of a cone. The cone is smaller than the original one, but it's in the shape of a cone, and there is a formula that tells you the volume of a cone. If you don't know that formula, you're going to look it up. I'm going to tell you what it is for now. The volume of a cone is 1/3 pi r squared times h. That's V equals 1/3 pi r squared times h. Pi r squared is actually the area of the top. H is the height. And so we really have the area of the top times the height, but we multiply by 1/3. Now you see the volume is a function of both the radius and the height at any time. We want to know the rate of change of the height. We could do this problem the way it stands, except we would need more information because the relationship between volume, radius, and height could be differentiated with respect to time, and we could get a relationship between the rate of change of volume, the rate of change of radius, and the rate of change of height. But we're not given that much information. However, you see, there is a relationship between the radius and the height that comes from the diagram. If you look at this cross-section, you see that this large triangle and this small triangle are similar. Sides of a similar triangle, or sides of a pair of similar triangles, must be in the same proportion. In other words, we have r is to h as 4 is to 12. So the relationship between r and h is r is to h as 4 is to 12. Or in other words, r over h is equal to 1/3. Now we look back at the problem, we see that the information we're given is in terms of h. So what I'd like to do is get r out of this formula for the volume and replace it by its equivalent in terms of h. That means I'm going to take this equation and solve it for r in terms of h, which I can then substitute into the equation for the volume. Since r over h is equal to 1/3, I multiply by h, and I get r is equal to 1/3 times h. Now, substituting into the original formula, I get the volume is equal to 1/3 of pi times r squared, that's 1/3 h, the quantity squared, times h. That is, the volume is 1/3 pi times 1/9 h squared times h, or in other words, the volume is 1/27 pi times h cubed. And now we're back to a situation like the one we had in our first problem of the helium balloon. We have the volume as a function of a single variable. Both v and h are functions of time, and we can take the derivative and substitute our given information. So let's take the derivative. dv dt is equal to 1/27 pi is a constant. The derivative of h cubed is what? Well, it's 3h squared times the h dt, because h is a function of time. 3 times 1/27 is 1/9, so we get 1/9 pi times h squared times dh dt. Now, let's see what kind of information we have. We're told that the water is flowing out of the reservoir at a rate of 12 pi cubic feet per minute. That means dv dt is minus 12 pi. So dv dt is minus 12 pi. We're asked to find the rate of change of h with respect to time, dh dt, when h is equal to 9 feet. So h is equal to 9. And now you see I'll be able to substitute for dv dt. I'll be able to substitute for h, and we'll solve the equation for dh dt. Now let's see. Substitute the information. We get minus 12 pi is equal to 1/9 pi. H squared, that's 9 squared, is 81, times the h by dt. 9 divides into 81 9 times. There's a pi multiplier on both sides of the equation, so we can divide that out. And finally, we get dh dt by dividing by 9. Minus 12 divided by 9 is minus 4/3, or minus 4/3.
When you're serious about learning an academic subject or scoring high on a test, there's just one name to know: video-aided instruction. We don't waste your time with goofy skits, corny jokes, or silly sing-alongs. We get right to the point. Real teaching by real teachers. Visit us online at videoaidedinstruction.com to learn more about our exciting line of educational programs. As we say here at Video Aided Instruction, press play to learn.
Do you want to earn better grades in school or boost your scores on standardized tests? Do you want to increase your fluency in English or improve your communication skills at work? Or do you simply want to relearn those forgotten grammar rules? Well, look no further. Video Aided Instruction's English Grammar Series is a great resource for everyone, whether you're new to English or you've been speaking it for years. Our one-of-a-kind series can help you master even the most complicated grammar topics. Be sure to view the entire series: English grammar sentence structure, parts of speech, sentence complements, verbs, pronouns, agreement, modifiers, parallel structure, punctuation, and spelling and capitalization. So don't let mistakes in English grammar embarrass you or hold you back. Let video-aided instruction help you eliminate them from your speaking and writing forever. Do you want to get your GED? Well, you're in luck. Video-aided instruction makes it easier than ever before. Our one-of-a-kind series prepares you for even the toughest questions on the 5 GED tests. Be sure to view GED Language Arts Reading, Language Arts Writing, Mathematics, Science, Social Studies, and Calculator Essentials. Let us guide you toward that all-important diploma, a better job, and of course, higher self-esteem.
If you find studying for the GED overwhelming because you don't have basic reading, writing, or math skills, then Video-Aided Instruction's Pre-GED series is exactly what you need. This series makes the fundamentals much easier to understand and master. You'll want to view pre-GED language arts reading, language arts writing, mathematics, science, and social studies. Our pre-GED series is a great first step toward GED success.
A true industry pioneer, Video-Aided Instruction was founded in 1983 by two former teachers from the New York school system. Over the years, our academic courses and test prep reviews have helped millions expand their knowledge and improve their lives. Today, our state-of-the-art studio and production facility is located in Hicksville, New York on scenic Long Island. Educators and students the world over recognize the Video-Aided Instruction brand of academic instruction as the most comprehensive available. Whether you want to brush up on your algebra or improve your skills in English, earn your GED or ACE the SAT, serve your country in the military or pursue a graduate degree, or learn a wide variety of other subjects, Video-Aided Instruction has a program for you.